Today, I just selected a sample given the time constraints. So cross-modal learning in cognitive robotics. So actually, this is a highly relevant thing in robotics, because basically we need to combine information if we want to apply this embodied cognition approach going from bottom up. So data coming from different modalities have different properties, and they have naturally be combined in some way. And technically, you can do it in different ways, as you can see there. So Gabika already mentioned these autoencoders, in particular variational ones, which is a type of a neural network that's trained with self-supervision, supervised learning based on gradient descent, etc. It has generative properties, which is nice. But there are other alternatives which you can use, like heteroassociation between two modalities. So one modality is X, the other one is Y, and you have to connect them somehow. You can even do it without a hidden layer, like by Hebbian learning, but that's very simple. It's better to include like hidden representations there and train it with various ways, like UBAL that I'm going to present. That's our model. And yet another third option is completely unsupervised, like having one or two modalities in X and train them by unsupervised way to a Y representation, something that we did, for instance, with Michal years ago. So today I will focus on the second part, this UBAL-based heteroassociation, connecting the two different modalities, and try to explain how it's done. The predecessor or the ancestor of the primary model was this BAL, as you can see there, which we designed, well, almost a decade of years ago, where you have one layer, the second layer, and the third layer, the three layers, and they are connected with in both directions. So there are, possibility to retrieve Y from X and X from Y. And this type of an algorithm is not trained by backpropagation, but using these learning rules, which I don't have time to explain in very detail, but just if you look at these equations, so these are the classical perceptrons. So you submit an input X here, and propagate the activation in one direction, and then you go from the other direction. But the point here is that these both layers serve as each other's targets. Okay, so you can look at them as they train each other mutually. And the concept of this learning, if you look at this, so whatever weights you look at is basically trained on this. Actually, the Hebbian term, that's a product of two components, the product of one activity multiplied by the difference of other two activities. And it always concerns that a presynaptic neuron and postsynaptic neurons. So that concept does not depend on like any gradient propagation. It's very, I would say, biologically relevant. So, but this was a very simple version that has some limitations. Therefore, later we came up with a more complex model that has the same architecture. It has one hidden layer, but doesn't have to, and it has the same everything in the previous method had, but it also has this concept of echoes. That means that when you take an activation here, you propagate it here, but you also take an echo, and that is pretty completely symmetric if you look at that. So it's much more complex. If you look at the equations, they are actually, there's a number of equations, but there's a lot of commonality. If you look at the structural, similarities, the way the information flows, it would take time to explain it. But if you look at it, on the surface value, how these weights are changed. So actually, there are 4 weight matrices. So these two are for that direction, and these two are for the other direction. So they are trained, all of them. And if you look at this, so I mean, it pretty much resembles the previous model, the simplified, again, a product of two things. But here, the meaning of those is much more complex. Okay, so for instance, here are those echoes. So it simply means that in this type of model, you get a more closer link between the two modalities or two sorts of signals, and in a way that they are more closely sort of linked with one another at the hidden layer. So when we wanted to use it, so for instance, as a small example, the first model, this one. So if you have a simulated ICAP robot, so for instance, one of the basic tasks is if it's if it wants to look into its palm, center of the palm, so it's looking into its hand. So, for instance, when if the robot wants to fix on this, it can move its arm like this, and it will track. It will track. So actually, we are linking the proprioceptive information from the head, combined with eye gaze, with the proprioceptive information about the hand. How the hand is positioned. So there are two options how you can do that. Model A is simpler, so it means that you cannot move your eyes, so you have to keep your eyes gaze fixed, and you just do this. So there actually have one-to-one mapping, with one exception that if I do this, there's ambiguity because it's always the same head position. But other than that, it's one-to-one. If you take model B, it's more complex because you can look into your palm, not actually having your head face there, but I can do it like that. So I can, there's a combination of two sources, like my head position and my eye gaze. So both possibilities work to a certain level of accuracy. And so one can take an UBAL for this. So if you take just this model, you just have the pairs of these values and just establish the mapping that's bidirectional. You can treat one from the other and vice versa. So so the model is very simple. Like you needed to collect some data pairs, and I mean, using this training, it's very fast. So you just need to have a very small network. So for this A model, you just need 7 degrees of freedom. That's for hand position, and just 2 degrees of freedom for head position, like pan tilt. That's all, and just 20 hidden neurons. And if you just evaluate the accuracy, you see there are some errors, like few centimeters, but of course maybe a more complex model would do a better job, I would say. But as a proof of concept, I think that's sufficient. So we can retrieve. So when I have my eyes closed, so I can predict that. I mean, I could predict if I'm looking there, where my head should be, where my hand should be. So if I provided the head position, I know this. And if for instance, if I have my head here and I'm looking there, I know how to turn my head in order to be looking into my palm. So now let's move on to the second model, which is more complicated, towards body schema in robots. So now we want to link other modalities, not vision. We know that representing body in the brain is a crucial thing. So for any agent, like humans, we somehow have to learn it, how to represent the brain, the body. And there are two important concepts that are established in the literature: this body schema and body image. It's not clear, I mean, how they should be differentiated, but body image is something more visually oriented, like how my body looks like, but body schema is more functional, multidimensional, so it includes also proprioception. So if I close my eyes, I know how my legs are positioned and also any part of my body, for instance. So these body representations are inherently multimodal. There are all those modalities listed there. And among those, this somatosensation is something that starts to play a role very early in life. So actually, it's the combination of tactile, touch, and proprioceptive information, body position. So these two modalities are very crucial. They start to develop very early on, even before birth, and during ontogeny, when the child is born or baby is born. So self-touch is something that plays an important role. So the baby learns about its body by touching itself, right? It's not starting random, motor babbling, etc. But then it becomes more goal-driven. So just to illustrate some basics here. So if you want to associate proprioception with touch, so on one hand we have proprioception. So for the ICAP robot, which is not seen here, but actually there is a silhouette of this robot, it has 53 degrees of freedom in total. Okay, so I mean the position of a body is actually a point in 53-dimensional space. On the other hand, touch can be represented in a robot. So fortunately, this ICAP already has a skin. That's the one. There's one in Prague by Maciej. Maciej has one, Maciej Hoffman. And so they developed this, also working with a simulator of this ICAP, and this is the skin. So when the ICAP touches itself, so there are, the corresponding touch areas activated. And this is biologically motivated. So the tactile stimuli are represented in a map. So we know that the area 3B, we have this somatosensory homunculus. So when I'm touched somewhere on my skin, So the certain neuron represents the activation, like letting me know that I've been being touched, right? So that's relatively clear that we have such a nonlinear warped body surface in this cortical area. But when it comes to representation of proprioception, like body position, it is much more complicated. It's known to be somewhere also like 3A area, area 2, and it's in the brain. It's very closely related to this, tactile. They are sort of connected with one another, but there's no clear understanding how that should be represented in the brain. How should we do it like technically? But we had to come up with a decision anyway. And so when it comes to again, so on the right there is this the ICAP that has learned how to represent the touch. So it's like pretty much bio-inspired. So this is how it's known to exist in monkey. So in a robot, it's very similar in a topographic way. So when a robot is touched somewhere, so the corresponding neuron fires. So that's one like partial result that's crucial here. And this is achieved by using self-organizing maps. So self-organizing map is a well-known unsupervised algorithm that allows you to build a mapping between the source domain, like high-dimensional inputs, to the target domain, which is two-dimensional map in a topographic way. In order to make it successful, like to preserve this topographicity, one has to make some tricks like using the masks, which is something like receptive fields of the neurons. So not all neurons see all parts of the skin. So in such a way, we introduce constraints and how it can be mapped properly. And that was with certain tweaking, it was made to work. And here, when we link the two modalities, so actually this is the entire model. So on one hand, there's the proprioception, which had to be somehow solved. So the suggestion coming from our minds was, okay, let's split it to a number of SOMs, classical SOMs. So for instance, each arm, like the left arm, which has 16 degrees of freedom, so the whole arm plus fingers. So it was split like in two arms. This would be one SOM, and this is the other SOM. So one subspace, the other subspace, both were mapped to the 2D space, and they were trained a priori. On the other hand, the corresponding touch data means that the whole touch area was split into 4 MRF SOMs, so like sub-representations. So in the first place, the data had to be collected somehow. So the training was based on like kind of motor babblings that the ICAP was sort of moving its arms. And we know that some configurations, some proprio configurations are touch-based. So this is touch, self-touch. Most of them are non-touch, right? So in order to make this work, you need to collect only touch data. So to have to identify those positions that are touch-based. So the touch could occur anywhere on these palms, but also forearms. And it's always, each self-touch results in 2 touches, right? So I'm touching with my left finger, my right forearm. So the touch occurs simultaneously in both SOMs, both touch SOMs. So that has to be, and that has to be somehow linked. So, I mean, when I close my eyes, I don't need, the vision is not needed there. So this is before vision enters the scene. The goal here is to predict from the proprioception to predict the touch, localization of touch somewhere appropriately. So the examples of these representations are shown here. So for instance, this is a subpart of a certain proprioceptive SOM. So this is like 6 by 6 neurons, each representing certain proprioceptive configuration corresponding to the left hand. So you see the left hand from an ICAP's perspective, you see that's the position of the hand. It varies. You don't see it maybe very well, but it's topographically organized. So you can think of this as each neuron is sort of representing certain maybe convex subspace, like this area, etc. Yeah, in this working space. At the same time, on the other side, this touch-based self-organizing map, again, the number of neurons. And what you see here is again, these are neurons that are corresponding to touches related to fingers because it has 4 fingers and one thumb. So the yellow area means the dominant activity. So actually these are receptive fields of those neurons. So this is all finger-based neurons sensitive to finger, at least, one finger or maybe sometimes 2 fingers, like in this case, 2 fingers. And these are all neurons that are sensitive to one of the 4 tactile locations on the palm. So it's like divided by 4 positions here. So 1 or 2, but you see it's not random, it's well organized. So we have such a discretized organization of both spaces, and in that way you provide these intermediate representations regarding the winners as inputs for the UBAL that can learn to connect the two. And in such a way you can test it in various ways. So this is just pilot testing, that if we assume some proprioceptive representations. So there are 3 examples. This is proprioceptive representations in 4 SOMs, proprioceptive. This is the corresponding touches. So always there are 2 dots out of 4, depending on where the touch occurred. So this is the second example. So of course, it would be nice to see where it actually is located on the skin. We don't have it here, but these are just internal representations like produced by UBAL. But from that, it would be straightforward to retrieve from the weight vector the corresponding touch position on the skin. And there are some numbers telling us that, okay, it's not that bad. I mean, the testing accuracy is always about 90%, so which is relatively okay. So these are pilot results, and in conclusion, we presented this UBAL as a bio-inspired learning algorithm for training a bidirectional neural network model. It's bio-inspired, so no backpropagation. It's Hebbian-like learning. There are possible generalizations to this. One could include also more than 2 modalities, like Gabika was saying. Here it's also a principle that you would have, like in a triangle, 3 modalities, and they would be training each other in all possible ways. One could also use 2 modalities with more than 1 hidden layer. We haven't tried it, but I don't see the problem why it could not work in using the same logic, because those are very general learning rules. I think in general, bio-inspired learning is useful because I think it is still something we can learn from nature for various reasons. That's a matter of discussion, of course, if longer explanation is needed. There are some open questions here that I can see, for instance, how to represent proprioception. So that was just one solution to break it down to 4 subspaces, but we don't know, nobody actually knows how the brain does it. So one just has to work with some hypotheses if one wants to include that modality. And I think that modality is crucial, proprioception. And even more important question is how to integrate those modalities. So here, we just take them as they are. So I mean, the dimensionality here and here can be different. If we are merging them in a autoencoder, I think this is more difficult because there you have like different quantities, different amount of information is entering, contributing to the latent representations. And I think that the brain somehow has to solve this by some maybe adaptive mechanisms, how to do it. We don't know for sure, but definitely that's worth investigation. I didn't talk about deep learning here. Now everybody uses it. Of course, sometimes it's reasonable, but I think we can find principled solutions also with simpler models, especially if we want to understand truly how things are being done. It's also related to this cognitive robotics. Now we talk about explainable AI, about trustworthy robots, etc. All that assumes that we have to truly understand how these models work. We have a number of visualization, computational methods, how to look into the models, which is very nice. And these generative models, which I didn't talk about, this is a discriminative model, passive models. I think these generative models, they provide this added value by having this generalization, this generative thing, but maybe they also have some problems like lack of control over the generated examples. But I think, so it's a matter of choice what one uses, because I believe that also discriminative models can make some generalizations, some can have some generative properties.